upsets you with the fact that it sounds sort of impossible. How can Alice and Bob don't trust each other at all? They're willing, Alice is willing to, Alice has a program she wants Bob to execute, but she can't trust him. She doesn't even have the capability to run any execution that is as long as the running time of Bob. And Bob, on his side, has private information he cannot reveal to Alice. So how can they convince each other that the output is correct? I hope you see that it's sort of mystical and magical how this can all happen. Now, if you go out there, I mean, you know, Bitcoin and other things in security and cryptography are based on a lot of beautiful work from the 1970s, like public key cryptography, hash functions, and other things like that. And there are a lot of implementations and a lot of things out there that use them. If you go and then look for downloading software that does zero knowledge or probabilistically checkable proofs, today you won't find it. Our point is that, you know, by the end of the summer you will. And the reason it's not been fully implemented so far for standard C or Python programs is because of efficiency problems. So while the theory in math is really beautiful and nice, it's very hard to scale it down to make a system that's working. And in particular, if you want to achieve all of these, you want universality. You want it to be something like a compiler that works for any program, not just for one typical thing that you did. And you want to have minimal costs, both for Alice and for Bob. And you want to have a minimal number of interactions. You don't want some convoluted protocol that Alice and Bob send messages back and forth. You want something that's as short as a signature. You want all of those, then getting it into a working system is a big, big challenge. That's why, you know, the spectacular works about zero knowledge proofs and other things are already 30 years old, but they haven't been implemented so far. And our main contribution, and that's what I'm telling you about, is that we actually solve this sort of theory to practice challenge. There have been, in the past, a few implementations of parts of things, either computational integrity or computational privacy, in certain settings. And there's a list of works there, but also the slides on, and you can check the references there. Our main advantages, the main advantages of our new system are, first of all, universality. We'll start with standard C programs, you know, with loops and arrays and memory allocations and everything. And it will be succinct, so the cost of Alice will be much smaller than the running time of the program. And the cost for Bob will also be manageable. So Bob has to put some extra effort in order to generate the signature, but it will be something manageable. In particular, it's close to the running time T. Polylog means there's T multiplied by a polynomial times logarithm of T. So if T equals something like 2 to the 32, log of T is 32, and if the polynomial is something like squared, then that would be 900 times the running time, times 2 to the 32. To compare this with previous solutions, at the very least they have to run in time T squared, which T equals 2 to the 32, that brings it up to 2 to the 64, which is a little bit worse. So, I just want to give a little bit more details on the sort of asymptotic mathematical scaling of the system. Then I'll give you some numbers of what you can expect to see in the context of Bitcoin. So bear with me, this is a little bit more theoretical than most of the works you see out here, but let's just suppose that the program is S bits long. So let's say just 1,000 bits, and the execution is much greater than that. Maybe it takes 1,000,000 steps, okay? So the minimum possible costs on both sides, Alice must at least send the program to Bob, and that's going to be at least 1,000 bits worth of work. And Bob must at least execute it, because otherwise we'll be contradicting the undecidability of the halting problem. So Bob must go for time at least T, and then he responds to Alice. And what we achieve in our system is very close to that. So the cost to Alice is going to be very close to S. It's going to be a small polynomial in S, and we'll have benchmarks to see how small it is. But it's really quite efficient. And the cost to Bob is, again, very close to T log T. It's going to be something like T times log T squared or cubed. And again, we'll have benchmarks to see how it works. So how do we do it? You're probably trying to think, well, how do I sign it? So you're thinking, well, let's take a hash or something like that, right? And then this is something that, say, antivirus programs do, right? You take a large file, and then you compress it into some cryptographic hash, and you sort of send that, right? And then, if someone wants to mess with the program and change a binary in any way, then the hash just won't align with that. Well, it's a good start, but it's a long way to the actual solution. And the reason is that what we're really signing is not a binary of a program, but a whole trace of an execution. And we have to check that every step in the execution worked well and sign that. So it's a much more complicated kind of cryptographic signature. Okay? So in particular, it's all available on my webpage. It's all publicly available. You can read it. It's going to be hundreds of pages of advanced theoretical computer science. But I encourage you to read at least the introductions and see some of the talks on it. But the point I want to get over to you is that it's a little bit like the case of the fast Fourier transform, another very advanced algorithm, where the mathematics that underlies it is very complicated, and making progress on it is very hard. But at the end of the day, it translates, like the FFT, into very efficient algorithms that you can say run on your mobile app. In the case of FFTs, when you're listening to music or downloading a movie, there's a lot of FFTs going behind the scenes. The math is very complicated, but the implementation turns out to be rather sweet. So it's the same in our case. And as I said, our system uses a lot of very famous works, just huge breakthroughs in theoretical computer science, and I encourage you to look a little bit into more about that. There are a lot of Wikipedia pages describing these things, such as checkable and computationally soundproofs and so on. Before I tell you a little bit how the system actually looks and works, let me tell you who are we. It's not myself. I have a pretty big team. Started with a very nice grant that I received from the European Research Council in 2009. And we used this grant together with my co-leader, Professor Eran Tomer from Tel Aviv University. We started to implement it in the summer of 2010. And the first thing was to scale this lofty theory down to practice. That led to a number of publications, again, available. And we did some work there, and now we're starting, over the years we started to implement it, and we have a pretty large team working on it, which sits all over the place. There's a large team at Technion, a bunch of us are sitting at MIT, including myself right now, at Tel Aviv University. And we have ongoing meetings by Skype and so on, so it's just picking up pace. So, in terms of, say, things to look for in the Bitcoin world, if you want to try and play with this, phase one, which I'll describe soon, is going to appear within a few weeks. We have a hard deadline presenting it at the conference on cryptography. It's going to be in Santa Barbara in August. You're all welcome to come in and see it. And we'll put things online, hopefully much before that. So by the end of August, there'll be some documents and some source code to look at. This phase one will have an initial setup cost to run the system for a particular program of roughly T log T. And I'll show you in a minute how it's going to work. And the cost of log is going to be T log T, which is the running time of the program. But the cost for Alice to verify, again, integrity of a computation in a way that doesn't compromise the privacy of Bob's private auxiliary inputs is going to be really minimal. This is going to be like downloading 10 kilobytes for even for a very long program, and then verifying will take something like a second or a few seconds on mobile app. And phase two later this summer is going to have the cost for both Alice and Bob completely optimal. So let me just show you how the system is going to work in phase one, again, coming in a few weeks. You'll start with an arbitrary C program, originally some standard version of C, C99 or something like that. And the first thing you'll do is throw it through a new compiler, a new